Example 3. Algebraic representations of rotations. When points are rotated about their origin, the coordinates of the image can be found using the rules in the table. Rotations: 90° clockwise. Multiply each x coordinate by -1. Then switch the x and y coordinates. So xy becomes y negative x. 90° counterclockwise. Multiply each y coordinate by -1. Then switch the x and y coordinates. So xy becomes negative y x. 180-degree rotation. Multiply coordinates by -1. That is, multiply each coordinate x and y by -1. So xy becomes negative x negative y. And also, don't forget, 270 degrees counterclockwise is equal to 90 degrees clockwise. 270 degrees counterclockwise is equal to 90 degrees clockwise. A transformation is a change in a figure's position or size. Translations, rotations, and reflections are types of transformations. A rotation turns a figure around a point, called the center of rotation.
All right, let's try one last movement around the plane, if you will, one last transformation. So I'm given this triangle, x, y, z, and here we're supposed to graph and find the coordinates for the vertices of the rotation. Now, rotation means that we're going to take it and kind of pivot the object somehow, and let's see how. So we're going to rotate this triangle, x, y, z, 180 degrees clockwise around the origin. So what that means is you think of the origin as kind of like the center point, and now we're going to take this thing, and of course, you know, clockwise means that we go in this direction, and we're going to go 180 degrees, which means kind of halfway around. And what happens? Not so easy to see what happens, but let's just try it. Actually, I've got a movable triangle right here that's exactly congruent, so you put it right there. And then what we do is, you imagine like putting a pin or something literally right there at the center, like that. See that? Boom. And I put my finger there, and now 180 degrees. That means that I go, let's see, it's kind of neat because you can really see the movement. It's kind of interesting. This, by the way, is just 90 degrees. That's 90 degrees. That's sort of halfway. But we're going 180 degrees clockwise around the origin. And then look what happens. You get right to here. Yep. And there we have it. So you can see exactly where the figure is. Kind of interesting, actually. Not so clear. Let's see if we can actually label this correctly. All right. So I've got to label an x prime, a y prime, and a z prime. The way to do that, by the way, is maybe just take the point and kind of follow it. So here, that's x, and where does that go to? That's the highest point. So when I go way over here, it's going to be the lowest point. So that's going to be x prime. This point is the furthest point to the left, which means that when I rotate it 180 degrees, it's going to be the furthest point to the right. So this is going to be the z prime. And therefore, this better be the y prime. Let's see. It's close in here, y prime. In fact, just thinking those thoughts actually helps me with the rule that will, in fact, produce the coordinates, even without graphing it. So what we do is we take the coordinates, and what do I want to do? Well, here, since I'm actually rotating around the origin 180 degrees, notice what happens. That not only does the x value change sign, but the y value also changes sign. So the x value flips and the y value flips. And so what I have to do here is I have to multiply both the x and the y value by -1 in order to change the sign of each. So the corresponding value for x prime would be, coordinates would be -1 times -3, and then -1 times 4. Because, by the way, the coordinates of this point, you can see, are -3, 1, 2, 3, 1, 2, 3, 4. So there's that, x. And what does this give me? This gives me an x prime having coordinate -1 times -3 is 3, -1 times 4 is -4. Does that check? Let's see. 3, 1, 2, 3. 1, 2, 3, 4 down, so that's negative 4 x. And this goes on. Y prime would be negative 1 times this negative 1, negative 1 times 0. Again, I multiply both coordinates by negative 1, do that 180 rotation around the origin. So I see y prime has coordinates 1, 0. Does that check? Yeah. 1, 0. There it is. And then finally, for the z prime, same rule. Negative 1, negative 1 times negative 4, negative 1 times 0, and we see that z prime is going to be this time 4, 0, and that's exactly what we see here, 4, 0. And so you can see we have it. We've actually found the coordinates, not just by reading off, because this graph might not be perfectly accurate, but just using the facts we're given and reading off the coordinates of the original geometric object, in this case a triangle, we were actually able to rotate it and use a rule to find the coordinates of that rotation. Congratulations on moving things about the plane. Have lots of fun with it and enjoy finding those coordinates via the rules for yourself. I'll see you soon.
Now don't forget, in this particular lesson, 9.4, it was basically a repeat of 9.1, 9.2, and 9.3. However, the emphasis on this particular lesson was being able to write the algebraic rule. This section right here, being able to write the algebraic rule from what you've done. Okay, being able to write the algebraic rule. Here the rotation was 180 degrees, and the algebraic rule is we must multiply each x term, excuse me, let me get down here, 180 degrees. We must multiply each x and y term by a negative 1. So negative 1 here, negative 1. Right here is the rule that we're writing. You have to know the rule, but right here is what we're writing. Also, don't forget, even though we showed you this, I think, 2 or 3 times already, don't forget 90 degrees clockwise is the same as 270 degrees counterclockwise. 90 degrees clockwise is the same as 270 degrees counterclockwise, right? So these two are the same, and you use the same algebraic rule.